Hello everyone, and welcome to Linux Forensics here at Pentester Academy. In this video, we're going to start talking a little bit about memory forensics. So this is something that a lot of work has been done with recently. Some of you may be familiar with a product called Volatility. It is essentially a collection of Python scripts that allow you to examine things from a memory dump. Now recall that way back, 40 videos ago, maybe it was more than that, we created a memory image of our target system. And now we're going to show you how you can use volatility in order to examine that. Now on the Linux platform in particular, before you can do anything useful with volatility, you need to set up a profile. And the reason for this is that every version of Linux and every kernel version could be slightly different. In order to make sure that you have the exact right structures in volatility, you have to create this profile. So how is that done? That's done by compiling a specific program and creating a dwarf file and also getting the system map file and zipping that all together. So if this sounds complicated, it's because it is, but you're in luck. I've written a very simple shell script here that will help you out with this. So how does this work? We have our standard shebang bin bash. Our usage says this is for creating a volatility profile from a mounted image file. And what you do is you call it and you give it the path to the root of that image file. So if it's mounted at media part 0, that's what you would give it. And we'll see how this works in a little bit. I check to see, did you give me enough arguments? If you didn't give me enough arguments, I'm going to give you the usage statement. Here I store the current directory, and then I change to the directory you passed me /boot. Because in that boot directory, I will have my system map file, which will have as a suffix the version of the kernel. So to get that version, I do an ls for system map star, and I pipe that to sed, the scriptable editor. And I said, sed, please substitute system.map dash for nothing. In other words, please strip that off of my file name. And the results from these commands are passed back and stored in vir. I then cd back to my old directory. I echo the version. Recall, we've talked about this in previous videos. It's safer to put your variable name in the curly brackets. So that's what I've done here. I then get my current directory. I get my make command using which make, and I store those in some environment variables. Here I cat what's on the next line until I get to EOF down here, and I'm actually going to cat it not to the screen but to makefile dot the version. And this is my makefile that I've created and some simple rules. This I copied from the makefile that was included with volatility. I just modified it slightly. I then call make on my file, and I pass it explicitly this makefile. So I explicitly pass in a makefile name using -f. If you don't, make will expect a file simply called makefile with a capital M. Then I will copy the system map file. So I will copy again from the boot directory of my target, system map -vir to the current directory, and then I have to zip it up. So I zip it up into a file called Linux, then the version.zip, and what do I put in there? Module dwarf and system map version. Once I've done that, we'll show you in some future videos how you can use this in Volatility. For now, let me go ahead and run this. So first, I need to mount my image. So I'll call sudo mount image pi on our favorite image. Hopefully it's still your favorite image. I know we've been dealing with this one for a while. And if you're wondering, we will go back to some of these topics with another image or two for some more advanced attacks. You know, this case, it was a pretty simple attack, some attacks based on malware and some other things as well. So here I will run mount on my image file, ask me for my password, and sure enough, here I go. It pulled up and it mounted to media part 0. So now I will change to my new directory here and I will run create profile and I will tell it here's where you can get my stuff, media part 0. And sure enough, it's done. Here you can see my newly created file for my image. It was running a 3.16.0-30 kernel. So now that our profile has been built, we'll go ahead and copy it to the appropriate directory. And now if we have a look in that directory, we'll see two profiles. Here is a profile that we just built. And here is another profile for my current Ubuntu system. And that's all you have to do. As we said, we will talk more about how to use these profiles in some future videos. But that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Linux Forensics here at Pen Tester Academy. In this video, we're going to talk a little bit more about volatility. So first of all, what is volatility anyway? Well, it's an open source tool for examining memory dumps. And it allows you to examine Windows memory dumps, Linux memory dumps, and also Mac memory dumps. So I just browsed on over here to their page. It's volatilityfoundation.org. If you look at their page, you'll see they have references to the most recent version of Volatility, which was released with a really good book, The Art of Memory Forensics. You know, we're just going to hit some of the highlights of using volatility in this class. If you want to go a little further in depth, maybe some of the topics that we don't cover, in particular, we will not be covering Mac or Windows in this particular course. You might want to browse on over there, consider picking up a copy of their book, and kind of go from there. So back to our situation. We have a memory image, which we stored a long time ago. And so what we need to do is we need to take and run volatility. So how do you do that? Well, it's vol.py, and then you just run it. And if you give it the option --info, it will print a bunch of stuff. If you pipe that to grep on Linux, you should get a list of a couple of your plugins, and I do. Here we have it. We have two profiles. One of them is for a slightly different kernel, the -30 kernel, and the other one is -34. -34 is for my Linux system that I'm running this on, and -30 is something we built using our script from a previous video. So if I want to run volatility, I run vol.py --profile equals, and I'm lazy, so I'm going to copy and paste this right here, and -f, our image. My images are stored under cases. And here I have a ram.lime file. We talked about how we got this file in a previous video. and then I need a command. So I will start out by typing the command Linux underscore ps list. Please give me a process list. And here we have it. There are a couple of error messages about some plugins that it couldn't load, which actually don't affect us in our case. So if we look, we'll see our offset, the name of the process, its process ID, user ID, group ID, DTB, start time. So of course, init is process 1, which is owned by root, and then we see a bunch of other system processes. We see a thread process, some workers, a watchdog, etc. So we can see all these system processes being started. Then we see there are a few things being started by non-root users. And here, that's an interesting process. It's been started by the user 64K. It's an interesting user ID. And here we have our normal user. Our first normal user is usually 1000, and they've started a bunch of processes. And if we continue through this list, eventually we get to some interesting things like this. Notice this first process, Xingxi bind shell. So yep, sure enough, we have a rootkit process that's being run as root. Someone ran sudo and bash, and they have a root shell open, and we have a few other things as well. So that's how you use volatility. It's pretty simple. It's a little bit annoying sometimes because of these profile strings. Something you could consider doing with volatility, you could consider taking all of this junk and creating an alias. So you might just copy that and then perhaps in your bash file, your bash RC file, or somewhere else. And I'm going to edit my bash RC, and I'll just go to the end and add another alias. You can see that I already have one to update my system. And I'll say this one will be vol for Pentester Academy equals, in quotes, I'm going to add my string like so, and I'll write my file. Resource it, and now I can do something like this, VPA Linux underscore PS tree, and I get a different kind of display. So here I will get a process tree that is displayed for me. So now I'll run a process tree, and here I have my process tree displayed. And the way that this is done in volatility is I have periods that show a process that is a subprocess of something else. So you can see here I have a couple of subprocesses of the network manager, and there's a few a little lower down that have many levels. In particular, if I look at LightDM, which is a windowing manager, I will see that it has a bunch of subprocesses running. Of course, I could take this output and pipe it to grep, Xingxi, and sure enough, there I have it, my Xingxi bind shell. Well, that's all for this video. As always, if you're enjoying these videos here at Pentester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Linux Forensics here at Pentester Academy. In this video, we're going to talk a little bit more about using volatility to look at process information. So as a reminder, in a previous video, I gave you a little tip, and I said that typing in your volatility command string all the time is kind of a pain in the butt. So what we can do to make that better is to create an alias, which is exactly what I did. So if I look at my bash RC file, you'll see that I created this alias right here. So I'm running vol pi -- profile equals, and then the name of my profile for my target system, -f cases, and here's the path to my Lime file, which we created a long time ago in a video far, far away. Another thing that we introduced briefly in a previous video was the info command on volatility. So you can run vol pi -- info, and you can pipe that to grep. And in this case, I'm going to pipe it to grep on Linux in lowercase. I can also t that to a file if I would like. Maybe I want to call it vol linux txt. And that will allow me to have a list of my Linux commands and also to display them on the screen. So he said in this video, we're going to talk a little bit about some of these additional process commands. We talked about process list and process tree in a previous video. Great. So let's use some of these commands. We'll start by using the command linux ps-aux. Now this command works just like ps-aux. It's going to give you this nice full listing. It'll give you things like the command line that a process used to be started, which can give you important command line arguments and such. So I'll go ahead and run that. And here you see some interesting information. If you scroll through this list, you'll see a lot of processes from user 1000, our user John. And then here near the bottom, you'll see some interesting stuff as well. So here we have the Xingxi bind shell. We also have sudo-s and then a bash shell. So these are all related. Here's my rootkit. Here is someone starting a root shell, and immediately they have a bash process. Incidentally, if you look at this guy right here, you'll notice that this is where we made the memory dump. Right, so here's how we perturbed our memory just a little bit by inserting this module, which we built on another machine in order to get our memory dump, and we dumped it across the network. Other things that we can do. We can get the environment for each of our processes. Now, you might not want to do this for everything. Thankfully, there are some options to most of these. For example, if I rerun this command, the -p, and I say I only want 3027, that process only, please, then we see just our Xingxi bind shell process. I'm going to run ps-env, and here again, I'm going to limit it to a single process. I can get all processes if I want, but so that we don't get lost in all of the data, I thought it might be helpful to look at just the one process. So here's our shell. Here is the process ID, and then here's the environment. So you can see that the terminal has been set up a certain way. Here's the path that's been set to language of English US with UTF-8 encoding. Home directory, it's pointing to John's home directory, and you can see that the username is root, but it was being run by John. We also see bin singi is set up here as well. So that is the process environment. Again, we could do this for everything. So just to give you an idea, let's do that. And you'll see that some processes have not a lot of information for their environment. Some of those system processes with low process numbers. And then as you go toward user processes, you have a whole bunch more information. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello everyone, and welcome to Linux Forensics here at Pen Tester Academy. In this video, we're going to look a little bit more at processes. In particular, we're going to look at process maps and how you can dump a process's memory image to disk for some later analysis. And we'll also talk a little bit about finding some hidden processes. So let's start by making a process map. So as before, as a reminder, I have set up an alias. My alias is right here, so that I don't have to type this long command string every time. And I'll say VPA, and the command that I want in this case is Linux _ proc maps. And I'm just going to do it for one process. So I'll give it -p, process 3027, which was our rootkit. And we'll see the kind of output that I get. So here's my output. You can see that I have a process ID, and since I only specified one process ID, everything here will have that same process ID. And for each process, it says what memory space is it using. So here I'm starting at the standard place, 4 followed by 5 zeros. And I have a little bit of RAM. It's read-only and executable, which is fairly standard for Linux. And notice I have an inode associated with this process. And we've seen this inode before when we did our file system analysis, and we know that it's related to this rootkit. Then we have a read-only chunk of memory and a read-write chunk of memory. Now, one thing you'll notice about Linux is pretty smart about how it handles memory. So you don't often see read-write execute permissions on memory because that's a bad thing. Then people can inject stuff into your processes. So here we have our heap for the process. It's stored here. And then we have some shared libraries. We have libc that is getting a little bit of RAM. Then there's some more stuff related to libc, and then we have things related to LD. Then we have a stack and another chunk. And that's pretty much that. So that shows you, again, a little bit about each process, what other things are involved, what files are involved, including their inodes. and what chunks of memory are being allocated and what are their permissions. I can also take a process and dump it to disk, which can be very useful if I want to analyze this malware later. If perhaps I didn't know what it was. We'll talk about that later in this course when we start talking about malware analysis. But for now, just to show you how does this go, what you can do is just run volatility and run the command Linux _ proc dump. Again, you want to give it a process, 3027, and then give it an output location, an output directory with either -D or --dir equals. And I'll just send this to my temp directory. It runs and it tells me, here it is. Here's what the process ID was. Here's the address. Again, the standard address. And here I have my output file. So if I were to run something like xxd on that file, I'll just pipe this to more. You'll see, sure enough, here's an ELF file, which is an executable Linux file format. Now, a lot of this other stuff here doesn't look like anything because xxd is not decoding the assembly for me. But if you page through this, you will see references to things like LD. Recall from our process map that this library was being used. And we also see some references to libc. So all of this is not surprising. This is a pretty short little program. That's all there is to that. You can also use a command called psxview, which will try to find hidden processes. So let's go ahead and give this one a shot. So we'll do a VPA Linux _ psxview, pipe that to more, and here we have it. We have all of our processes. Are they in the list or not? Does it have a hash? And some other items as well. You'll notice that most everything is in the process list with a few exceptions. And those exceptions seem to be happening toward the end of my list. And it's telling me what's being run. Once again, I could take this command, I could pipe it to grep on 3027, and we can isolate just that one process and see what it tells me. And it tells me here's the process. In this case, it was in that list. It's not hidden somehow from the process list. All right, so we will see in future videos more things that you can do with the Linux plugins for volatility, but that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, tell a friend. We'll see you soon. Hello everyone, and welcome to Linux Forensics here at Pen Tester Academy. In this video, we're going to show you how to use volatility in order to get a little bit of information about bash and bash histories for currently logged in users. We've gone over this before, but just as a reminder, I set up an alias. The alias I set up is right here, VPA. And I set it to run vol pi -- profile, and then the profile for my system image -f, and then my image file. If I look at what's available to me when it comes to bash, the first command that I'll find is just called Linux_bash. So let's go ahead and run that. And I'll go ahead and pipe this to more. And we'll see the kind of information that we're going to get. So here we can see that this process ID, 2568, has a little bit of history. So they ran apt-get install, netcat, they ran an update. Looks like they made some directories. And they ran a few commands. It would appear as though one of the commands that this user ran was to go to the downloads directory and go to the Xingxi Quan directory, look at the README, and then they did a few other things, and then later we can see the user who is copying the lime for imaging this system, and there are a few other things that are being done. We can see where the lime module was inserted, and then the system was imaged. I'll just skip over some of the rest of this. And this is all in that one user process. And then we look, we see another process, 3035, and it was used for some other purposes. So this user ran nmap, and it looks like they were also interested in our Xingxi Quan rootkit. So this is interesting because this will give you a user's history. Now, you might say, but can I look in the history file? And the answer is yes, you can. However, a sophisticated attacker might disable the history or set the history file size to 0 so that all of their history is not stored. And this is coming from memory, of course, because it's volatility. And this will give you a different picture in case someone has tried to hide their actions. Another command related to bash that you can run is this one. So you can run Linux_bash env. Again, I'll pipe this to more. And this will tell me about the environment for each bash shell. So recall that we had just seen two different processes, and now we should get some environment information for those two processes. So here we can see for the first process, which was at process ID 2568, we can see some different information. Here's the shell. It's an Ubuntu session. And it looks like our user is John. If I look a little further down, I will probably see more. Right here, it says login was John. And then here for this other process, 3035, we will see the user in this case was root. So we had one bash shell being run by John and another one being run by root. Finally, there's also a bash hash, which will give you a little bit of information about the hash table from the bash process in memory, which is going to store things like recent commands, etc. So we'll let this run, and here you can see that sudo was run a few times, as was ls, and for this process they ran new name, probably trying to get the exact version of Linux, insmod, and ls. So that's just a brief introduction to some of the bash functionality in Volatility. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello everyone, and welcome to Linux Forensics here at Pen Tester Academy. In this video, we're going to talk a little bit about some of the volatility plugins that are intended to help you find malware and other issues on a Linux system. So I'm going to go through these somewhat in alphabetical order. So the first one I want to talk about is called API hooks. Now, by way of warning, a lot of these volatility plugins take a long time to run. So what I'm going to do is I'm actually going to use the time function in Linux in order to show you how long it takes to run these, but I will pause the video so that you don't have to sit here for many minutes while this runs. Now, just for reference, we have a 2 GB memory image, which is fairly small, and I am running this on an 8-core i7 system with 8 gigs of RAM, running Linux Ubuntu 14.04. So I should get some decent performance. Your mileage may vary, of course. So if you're not familiar with time, it's pretty simple. You just run time, and then you give it your command. So as before, I'll use my alias VPA, and I'll say Linux _ API hooks, and it will run and do its thing. And here we're just starting to get some results. So we've been running for hours now, and this one script is still not done. You can probably notice that it's a little dark outside. As I warned you, some of these scripts take a long time. In fact, I just interrupted this, and this is all the output we got in 174 minutes. So it really has been going on for quite a while, and it's been operating at essentially 100% CPU. So that's the API hooks check. Some other checks. There is a AF info check, and it will look at the function pointers that relate to network protocols. So if you suspect that someone has done something funny with your network protocols, you can give this one a try. So let's go ahead and have a look at this one. So again, it's Linux check _ AF info. And this is going to look at those AF network calls. And in this case, it returned a lot quicker and it found nothing. Another check function that is available in Volatility is this guy, the creds check. And what does this guy do? This guy will check and see if there are any processes sharing credentials, which could indicate some sort of malware. You know, you've got somebody that is trying to use someone else's credentials. In the Windows world, this is sometimes called a pass the hash or pass the token attack. And we see that we didn't get anything here. indicating that's not going on. You can also check your file operation structures to make sure that some rootkit hasn't been used to modify them. So the command for that is check fop for file operations. We'll let that one run. And this one is now finished in 2.5 minutes. Notice that we didn't find anything, which is not surprising given this particular subject. Incidentally, we do have some other subjects that are coming along later in this course. Our first breach was a pretty simple one, and we will do some work with some more advanced attacks later. And in that case, we would probably come up with some results for some of these. I just wanted to show you some of the functionality of volatility, and then later we'll kind of circle back a little bit and we'll delve a little deeper into some malware. Another thing that you can use is you can look at the interrupt descriptor table, and you're probably familiar with interrupts and what they do. So you can check to make sure that somebody hasn't messed with this interrupt table. Try to redirect people to something malicious. So we'll let that one run. And we see this one runs fairly quickly. In 6 seconds, we were able to get all of the different interrupts on our system, including everyone's favorite int80, which is a system call. And that's a system call that's used in 32-bit Linux and Windows as well. Other checks that you can make. You can check for some inline kernel hooks. Is somebody trying to hook some of those functions? Once again, we had the API hooks check for the userland stuff, and we also have similar checks for the kernel space. So we can say, is somebody trying to hook my kernel functions inline? So I can check my inline kernel like so. And we see that this check completed in just over 3 minutes. And once again, we didn't find anything here because we don't have that particular kind of malware. Another test that we can do is we can check our module list against the list in the system file system. Is someone trying to hide something? Something malicious, of course. You can't really completely hide, because even if you Trojan all of the utilities on a system, there are certain things that have to be stored in various parts of your Linux system. So we'll go ahead and we'll run this check. That one's pretty quick. And then once again, in our case, we didn't have any malware of this type. We can also check our system call table using Linux check syscall. This will iterate over our system call table, and we'll let this one run. This will take just a little bit of time as well. So here we're getting some results, and it's first going to iterate over the 64-bit system calls, and when it's through there, it will go back and iterate over the 32-bit calls as well. So that one finished in a little over 2 minutes. And finally, there's one more check plugin, and this one is called check TTY, and it will simply check and see if there are any hooks for any running TTY or terminal devices. And this one is probably one of the quicker ones, at 5.5 seconds. And it's basically saying, nope, everything looks good here. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Linux Forensics here at Pen Tester Academy. In this video, we're going to look a little bit at using volatility in order to get some networking information. As before, we're going to use our alias, which I've set up, VPA, that runs volatility with our profile, gives it our file, and then it expects a command. So all of our Linux commands are prefixed with Linux. Not surprisingly, I can run Linux ifconfig, and this will give me a list. And here you see my 3 network interfaces. I have my loopback interface, ETH0, which was pointing out to the internet, and then ETH1, which was my VirtualBox host-only network. I can also run a netstat command. So I'll just run that. That's Linux netstat. And here we have all of the different ports and sockets that are open. Now we see there's a whole bunch of Unix ports, TCP ports. I could, of course, combine this with grep. So let me do that real quick. Let me combine this, and I'll grep for TCP. And now we see our TCP connections. And sure enough, what do we see right here? I see listening on port 7777, a Xingxi bind shell, which was process 3027. Not surprising given what we've seen before. We know that that was the process number. I also see that there's an SSH server running, a CUPS printing service, an FTP server on port 21, and some other CUPS related processes. If I repeat this for UDP, I get just a few results. Not surprisingly, port 53 is being used for DNS. Now, here's possibly a more interesting result. What if I look for Unix sockets? Unix sockets are often used for internal communication on the machine. So we'll see that there's a whole bunch of processes that are using Unix sockets to talk to each other. And none of these looks particularly suspicious, but it is something to check because you might have some malware that is also using Unix sockets for communication. Part of the reason that a malware author might tend to do this is that these aren't things that a lot of times get checked. A lot of times people look at TCP sockets primarily, and they also might look at UDP sockets, and they're a little bit less likely to have a look at these to see some inter-process communication on the machine. Another thing that you can look at the net filter. So if I do Linux net filter, it will show me my net filter hooks. So I see I have a pre-routing hook, some other information that I can look up. I can look up my ARP table. If I suspect someone is doing an ARP-based attack, I can do Linux ARP. And here we see a few different processes that are being run, and we see the ARP table that is being used on our target. Another thing you might want to check, are there any applications using raw sockets? So we can use list raw for that. Again, another popular way to talk between applications is to use raw sockets. And we see here there are a couple of processes using raw sockets, but they're not particularly suspicious. You can recover a routing table using Linux route cache. That is if you have an older version of Linux. That's pretty much the main networking related plugins for Volatility. As we said, we don't see a lot of activity in this particular case, but some of the future cases that we're going to look at in this course, we will see a little bit more here. Well, that's all for this video. As always, if you're enjoying these videos here at Pentester Academy, please tell a friend. We'll see you soon. Hello, everyone. Welcome to Linux Forensics here at Pentester Academy. In this video, we're going to look at getting file system information out of Volatility. Now, at first, this might seem like a strange thing to do. You might say, why in the world would I get file system information out of Volatility? Well, one of the things that we'll see in just a little bit here is that many times file systems only live in memory. Definitely this is the case when you have a live Linux distribution that's being used, but it also is the case for things such as the temp directory. In most modern Linuxes, the temp directory is actually a temp file system, and it is stored in memory, and as soon as you reboot, it goes away. So let's start by seeing what's mounted. So again, we'll use our alias VPA, and the command is Linux mount, and this will print some mount information. And now that that's done, I can look at what's been printed, and I will see various file systems that are being used. Most of them make sense right away. We can see here, it looks like this user has an extra external drive that's being mounted. And that external drive has two partitions, one that is apparently fat and one that is ext4. Now, another important thing that you'll notice here, we have actually gotten some options. So we have options for all of these mounts. So why do you care about that? Well, you care about that for a couple of reasons. If someone is going to break into your system and do something bad, they might remount file systems or mount new file systems with different options, which, as we learned when we studied file systems a little bit earlier in this course, can really affect how these things are handled by the operating system. So we can see a few different file systems here, and there are several of these that are using a temp file system. So we have this guy under run, C group under sys, etc. So that is the mount command. Another command that you might want to run that's related to file systems is the enumerate files command. So what does this do? Well, this will actually give you a list of all the files that are currently being referenced in the file system cache. We'll use our alias Linux enumerate files. I'm going to go ahead and pipe this to more. And it takes a little bit while for this to get started. And once it gets started, we'll see a few files that are in the cache. And we see some system files, a bunch of device files, modules. We also see some files from the John user. So here we can see that he has a few files cached. Some of these do look a little bit strange. It's not strange that his bash history is there, but some of these other files are in fact a bit odd. Why does this guy have some library files in his home directory? That seems a bit off. He has a few other files. Why does he have a hidden local share directory? Here we can see in his downloads that there are a bunch of files associated with the Xinqi Quan rootkit that we detected earlier in our investigation. And here again, in our temp directory, we have a whole bunch of files. So we have files associated with our rootkit. We also have these files, which, not surprisingly, seem to be about the right numbers for some inodes where some of this stuff has been hidden on the disk. A bunch of devices, some proc files, some more sys files, this time for kernel stuff, some run files, and some more device files. So you can see that we have quite a few things that were stored in this cache. Now, of course, we just sort of paged through this. In a real investigation, you would probably want to send this to a file, and then you could use your fun tools such as grep in order to find something interesting. So those are a couple of simple things that you can do with file systems and volatility. Well, that's all for this video. As always, if you're enjoying these videos here at Pentester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Linux Forensics here at Pentester Academy. In this video, we're going to continue our discussion of file system plugins with volatility. And in particular, we're going to look at ways that you can actually recover some of these file systems that are based on the memory, or at least the parts that are cached. So how do you do that? Well, it's pretty easy. As always, we'll use our favorite plugin. So once again, this guy right here, volpy -- profile, and -f, the name of our Lime file. So I'll say VPA Linux, and now I want to recover file system. Unfortunately, this is an all or nothing kind of deal where you get the entire cached file system from memory. You can't just say, I only want part of it. So I want to go ahead and dump the file systems, all of them that are cached. And I first need to make a directory. So I'll make a directory temp, my cache fs. And now I'm going to run volatility, VPA, Linux, recover, file system, -D. I could also use -- dump. And I want to go to tmp, my cache fs. And as we can see in my case here, volatility nicely fell down. Came up with an error message and some of the Python code. So what happened? Well, it's one of those things where memory analysis is very fickle. So for whatever reason, this plugin, maybe it doesn't like the particular kernel that's being used here. If you look at what Volatility claims to support, they claim to support through 3.14. It's actually a 3.16 kernel. Sorry, that's the way it goes sometimes when it comes to using tools like this. Now, perhaps by the time you're watching this video, that might have changed and this might work for you successfully. So interestingly enough, we were able to run Volatility and enumerate over our files, but we weren't able to dump the file system. Now, there are some other things we can try. There is a module in Volatility that allows you to find files. And not surprisingly, it's called Find File. So if I want to find a file and optionally extract its contents, I can use Find File. Now, unfortunately, this doesn't seem to support wildcards, but I can use the information I got previously from my enumerate files, and I can use that in order to run Volatility on a specific file. So in this case, I'm going to run it on the Xingqi bind shell port file in the temp directory. And here it's telling me the inode number and the inode address and the file path. If I want to get the contents of this file, how do I do that? Well, I use find file again, but this time I will give it -i, and I will give it my address for my inode. You might say, why not the inode number? Well, that's not the way it works. That's the answer. You might say, why does it work this way? It is a memory analysis tool after all, so it's not surprising that it wants the address. I can give it a place to output -o, and I'll actually put it in the same place. I'll put it under temp Xingqi bind shell. And this would actually work better for me if I used a capital O. And that completes. Now if I cat temp Xingqi bind shell port, sure enough, it tells me, yep, it's using port 7777. Not surprising. So what are some other things that I can do here? So we've already seen that we can list files. We can even recover files using find file. It's not a one-step process, but you can do it at all. It's still pretty cool. You can also do things such as create a timeline. And how do you create a timeline? Recall when we talked about the sleuth kit, we talked about body files and how you can create a body file. So let's do that. And the plugin for that is actually called Linux dentry cache. And this will create a body file. So if I do VPA Linux dentry cache and I redirect that to a file, call it body.txt, then I should have a file. And it looks like once again we've gotten bit by a little volatility problem, which hopefully by the time you're watching this, maybe someone will have fixed this issue. It appears to not really like some of the more recent Linux kernels. So again, what's the lesson here? We've had a couple of issues in this video with volatility not doing what we wanted, but fortunately, in many cases, we can get this information somewhere else. We did some videos earlier where we looked at building timelines from the actual file systems themselves. And of course, that can give you a much bigger picture and a much more accurate picture, unless, of course, you're dealing with file systems that are temporary and only in memory. In that case, Volatility does provide us the ability to actually find those files and extract their contents which is something that we couldn't necessarily do with normal file system forensics. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon.